So we are now entering the second part of our lectures. So we start with a very interesting topic called concentration inequalities. So this is a very wild topic. It has several different definitions and different applications, but there's a common theme to all of this, and essentially we are trying to understand the random variable in terms of approximating it by maybe its expectation, maybe its median, plus something that should be small. So this is the common idea that we're trying to convey when we study concentration inequalities. Of course, this is very uh, unprecise, but you can think of a variable, for example, in the real line here, that has a distribution with a density that looks like this. So it has some sort of concentration of its mass around its expected value. So this is what we're trying to convey in general terms, but of course we have to specify exactly what we mean by this, what type of random variables we'll be looking at, and what we mean by small. And here, of course, we can always write this, and this is going to be another random variable that's going to be the x minus its expectation. But the idea is try to show that with high probability, y is going to be close to 0. So the probability that y is bigger than t is going to be very small in t. So this error, of course, depends on t, but it should be very small. So this is what we're trying to pursue. And of course, the idea of small depends on something, right? It's like when you say that a function is continuous, you first choose an epsilon, then you choose a delta. And if epsilon is never free to be chosen, if epsilon is fixed, even if it's 10 to the minus 100, it's still big, right? So discontinuous functions could satisfy the continuity if epsilon is fixed. But this, here we are requiring not the parameter to be included in the picture. So now we're really talking about the relation between this n and the error. So up to now it's very vague. So let's give a very concrete example. So imagine, for example, that xn is given by the sum, like we did in the martingales lecture, for I until from 0 to n minus 1 of psi I, where psi I are IID random variables and distributed according to Bernoulli P. So this is an example of a random variable that we are looking into in this part of the course. We know that the expectation of xn is going to be n times the expectation of psi. So we do expect it to be something centered around np. And we also know that xn over n converges to p almost surely by the law of large numbers. So we do expect, for example, if we use the weak law of large numbers, that for any epsilon around this, so this is going to be n times p minus epsilon, and this will be n times p plus epsilon. The probability that x is outside here should be going to 0 with n, and it's going to 1, that the probability that it stays inside the interval. So this has approximately 1 probability. But how close to 1? This is what we're going to pursue in this lecture, we're gonna look at the probability that xn minus its expectation is bigger than n times some t. And this, we want a very explicit bound. So we don't want just to say that it goes to 0. For every t which is positive, we know this goes to 0 by the weak law of large numbers. But we want a quantitative estimate. And now we're going to start giving quantitative estimates about this, starting with this simple case of the sum of Bernoulli random variables. So the first observation, if we look at the variance of xn, this is also linear because xn is a sum of ID random variables. This is also going to be n times the variance of xi1, which happens to be n times p times 1 minus p. Okay, so why is this good news? Because we know that x, the variance measures how much the variable deviates from its expectation squared. So since the expectation of xn is of order n, and the variance is also of order n, we already know that xn is going to be its expectation. So this is in very informal terms, right? It's going to be its expectation plus something of order square root of n, because variance measures the square of the deviation from the expectation, right? You remember that the variance of something is the expectation of that something minus its expectation squared. So the fact that there is a square here says that the deviation is of order square root of n. Another way to say that this is true is recalling the central limit theorem that says the expectation, that says that xn minus its expectation over square root of n is going to converge to a normal random variable. So this tells us that not only the variable, not only the variable is close to its expectation when we look at it macroscopically, like this is the expectation plus epsilon n, and the expectation minus epsilon n, we actually know that anything larger than 1/2 here is gonna contain most of the mass. So this is another way to interpret the fluctuations of the central limit theorem. But how can we use the information about the variance to control the probability of these macroscopic deviations here? So here is where Chebyshev's inequality comes to help. So the probability that xn minus its expectation deviates more than t, and here I'm going to write tn because we want macroscopic deviations. So this, we can take the square of both sides. So here we get the fact that we are taking squares makes the absolute value useless, right? And by Markov inequality, this is smaller or equal than the expectation of what's inside here, which is just the variance of xn, over the right hand side, which is t squared and squared, recalling that the variance is p1 minus p times n. We cancel one of the n's underneath and we get this bound. So okay, assuming not that x is a Bernoulli random variable, but every x that has a second moment, assuming that the expectation of x squared is finite, we obtained a bound on the deviation or a concentration inequality of x around its expectation that behaves like 1 over n t squared. So this is a nice first result, but I would like to push it a bit further, because in some cases this will decay much faster than polynomially in n. And this is the first thing I would like to tell you. I would like to show that in some situations we have exponential decay of this probability. And then the rest of the course, we're going to see several different statements of this exponential decay. So let's start with a simple calculation. So this simple calculation is inspired by the same strategy that we used before. So remember that before we were trying to bound, xn minus its expectation being larger than, say, tn. And the way we did this was to square both sides of the inequality. Here we had before an absolute value, but let's not put it right now. We squared the absolute value and used Markov inequality. But the trick is that as soon as this is, as soon as we apply any increasing function here, so if you have an increasing function phi on the left and on the right, we don't change this event as soon as phi is increasing. So what we can do actually is to choose several phi's and see what we get. So the first idea is phi of x equals x squared, and it has two very important advantages. So first is that the absolute value of x squared is just x squared. So this is one big advantage of this approach. And the second is that the variance, which is of course related to the expectation of the squared, the variance of a sum of independent random variables is the sum of the variances. So this is something that we used and is very useful. And if we are going to choose another function phi to put here, it's very important that it's monotone and also that it behaves well with sums of independent random variables or with the procedure that we used to construct x. And now I'm going to present one option, which is very smart, which is to take the exponential function. So let's suppose that to start with, the psi function, that the psi random variable, has an exponential moment. So this is finite for some theta. So if we definitely need this to continue from here, and again, x n is going to be the sum of psi n, psi I. So we definitely need this assumption to use the exponential as our phi here. So this probability is small or equal, is actually equal to the probability that the exponential of theta xn minus its expectation is larger or equal than the exponential of theta tn. So up to now, we are just using the fact that for positive theta, the exponential of theta x is an increasing function. So what we did here was legal. And now we can, for example, use Markov inequality straight away. And we get that this is bounded by the expectation of the left-hand side over the right-hand side. I'll write it like this. So this is just Markov's inequality. And I promised you that the exponential random variable, the exponential function here, was going to help us from here on. And the reason why it helps is because you remember xn was a sum of independent random variables. So let's write that sum. The fact that it's a sum, exponentials of sums become just products of exponentials. So here I'm using p, but I'll start actually using nu. So nu is the expectation of psi. So I'm not assuming anymore that I'm talking about a Bernoulli random variable. And here we have the same exponential. But now, remember that these are independent random variables. Therefore, these are independent random variables. And the expectation of product of random variables is the product of their expectations. Remember also that this is finite. So this is the product of the expectation we assume to be finite. Now, these are IID. Sorry, I forgot the I here. These are IID. They have all the same distribution. So this is going to be the expectation of e to the theta psi 1 minus nu to the n e to the minus theta tn. Okay, so if you look at what's here, you may recognize this as being the Laplace transform of psi minus nu. So I'm going to write this as the Laplace transform, but if you don't know or don't remember what the Laplace transform is, there's no problem. It's just it's exactly this definition. Laplace transform at theta. And here I'm also doing something else. I'm taking the n on the two sides and joining them together. So why am I doing this? Because now it becomes clear that if we make what's inside smaller than 1, strictly smaller than 1, we just obtained an exponential decay in n. And you see here there's no n inside anymore. All we have to do is find some theta. So find theta such that this is smaller than 1. So this is our objective now. And it's not going to be hard because we are going to do something simple. We don't want to have the best exponential decay now. We just want some exponential decay. And for this, I will recall some facts about the Laplace transform. There is another name for the Laplace transform, which is the exponent, the moment generating function. Why is it called the moment generating function? So the expectation of e to the 0 times something is, of course, the expectation of 1, which is 1. What about the expectation, the derivative of this function? So this is the Laplace transform, at the value 0. So this function that we are looking here, it has values 1 at 0. Since we're going to take theta small in this application, let's look at the derivative of the Laplace transform at 0. We want to understand how it behaves here. And what we can easily show is that this is just the expectation of the random variable here, psi minus nu. So this is a simple calculation. As soon as our hypothesis holds, that the exponential moment is finite for some theta, it's well defined in some interval around the origin, and it has a derivative, and the derivative is the expectation, which in this case is 0. You see that we are already subtracting the expectation from psi. So this is also 0. That means what I drew here is wrong. Actually, the derivative around 0 is 0. Then it could do whatever it wants. I don't know what it does. But the important thing is that around 0, we can say that L psi 1 minus mu is bounded by 1, right? This is the Taylor expansion, plus something very small times theta for all theta small enough. So we can put here a slope, a very small slope delta, and this is going to be bounded by this line here, at least close to the origin. So what delta are we going to choose? So just believe me, a nice definition to put here is t over 2. So now we get something, and we can continue our bound. So this is smaller or equal than 1 plus t over 2 theta. And the exponential of theta t, we're going to keep it. Sorry, we forgot the minus here. Theta t we're going to keep. And this 1 plus something is bounded also by e to that thing. Forgot the n. So e to the t over 2 theta minus t theta, which is just t over 2 minus t over 2 theta. And I'm always forgetting the n here, which comes here. So this was a lazy approach. You see that we started with a deviation bound, and we are looking first just at the probability to deviate to the right, but we could repeat the same argument to the left. It's a symmetrical argument. And after taking the exponential on both sides and using Markov, we only had to find some theta small to get an exponential decay. So we're not going to be looking in this course to polynomial decays like we obtained previously. We are not going to be satisfied with this. We're going to look to have exponential decays. Now, there is one question. Is this the best we can do? Here, at this point, we could have tried to maximize this, actually minimize this over theta and get the best decay we could. This is actually something we're going to do in a great degree of generality. But independently of this, it's important for this class just to realize that the exponential decay is what we are after, and it's possible to obtain. Here we proved it in quite some generality. And now I would like to just spend a little bit more of time showing that we should not try to obtain something better than exponential. So exponential is possible. It happens under this hypothesis of exponential moments, but more than this is too much to hope for. So this is the last thing I would like to say, just that exponential is the best we can hope. Let's go back to our simplest possible example, where the xi(y's) are distributed as Bernoulli random variables with parameter p. And what's the probability that, let's recall that p is between 0 and 1. And let's put here some small epsilon such that p plus epsilon is still smaller than 1. So what's the probability that xn minus its expectation is larger or equal than epsilon n? So this is, now we are looking for lower bounds to show what we cannot hope for. The probability that xn is larger or equal than p plus epsilon n, which is exactly something smaller than 1. So this will happen if, for example, all the x's are 1. Oh, sorry, all the xi's. So if xi0 equals xi1 until xin minus 1, they are all 1. This event is contained. If this happens, then xn is n, which is larger than p plus epsilon n. So this is definitely a lower bound. And this happens with probability p to the n, which is some exponential decay, right? It's e to some theta n minus. So here what I wanted to say is just that even in the case that the random variables are bounded, we can still deviate from its mean with an exponential probability as a lower bound. So we cannot hope to get decays that are faster than exponential. Of course, if the random variable is trivial, if this has distribution delta of 1, then we can get any decay we want. But as soon as there is some fluctuation, some possibility that the random variable assumes values in two sets, we cannot hope for a decay that is better than exponential. So this is the type of decay that we'll be looking at during the course. And in the next lecture, we're going to take more concrete examples. So see,